In this video, we're going to work example problems related to the early definitions and postulates that we just learned at the beginning of this geometry course in section 1.3. So postulates like through two distinct points, there's exactly one line. Or if x is a point on a line segment AB, then the length of AX plus the length of XB is equal to the length of AB. Or the definition of a midpoint of a line segment, or the definition of congruence of line segments and angles. So all of the postulates and definitions and the one theorem that we went through in section 1.3, going through these early definitions and postulates that serve as a lot of the foundation to what we're going to learn throughout geometry. All right, so here we've got a line with points A, B, and C on the line. So AB plus BC is equal to what? And this notation here, that's the length of AB plus the length of BC is equal to, that's going to be AC. Okay, if AB is equal to BC, then B is the what of AC? Well, in that case, B is the midpoint of AC, of segment AC. Segment AC, if AB, the length of AB is equal to the length of BC, then point B is the midpoint of segment AC. Give the meanings of these four symbols here. So this is line CD with the two arrows. This is segment CD. This is the length of segment CD, and this is ray CD. Okay, now explain the difference, if any, between these different symbols. So okay, well, here we can come here first. The length of CD and the length of DC, that's the same thing. There is no difference. It's just however you want to express the length of a line segment. You could put the endpoints in either order. Here, this is the same idea. So you could say line CD. I mean, I guess we read left to right. Maybe you wouldn't want to say DC, but I mean, it's whatever you want to do. And similar idea with a line segment. I mean, we read left to right, so I guess you'd put you want to make it to where DC, you'd put D first, but it doesn't matter. Now, a ray is a little bit different because with a ray, you want to, it's going to be implied that if I say ray CD, then I'm thinking that the endpoint of the ray is at the first variable, and then it extends out through D. And if I say DC, ray DC, then that implies the endpoint is starting at D and then going out through C. So in this case, these would be two different rays. But, you know, it depends on the context as well. I guess if you have well, not really. I was thinking if you had a triangle, that the sides of a triangle or a polygon have, or line segments, but so if you have segment AB, segment BC, segment CA. I mean, you could say segment AC or CA. It doesn't matter, but that's the same thing. But, you know, when you're expressing the order of the triangle, the name of the triangle, you'd want to say A, B, C. You wouldn't want to, well, it doesn't matter with a triangle. If it was a polygon, you'd want to kind of state the variables in order. So if you had a polygon, so A, B, C, D, you don't really want to state this as whatever this is, A, C, B, D. You don't want to state it like that, but you could say A, B, C, D, or D, C, B, A, or this four-sided polygon C, D, A, B. And so in either direction you do it, you could, that means that the line segment is going to be, you'll have segment BC or segment CB. So in that sense, yeah, segment CD and DC are the same thing. Doesn't matter. Whatever you want to do. Same thing with two lines. Same thing with the lengths. Well, only with the rays is the order actually going to mean two different things. If you tell someone a ray with two letters like this, that's going to be implying that the first letter is the endpoint of the ray. Classify as true or false, looking at this reference here. AB plus BC is equal to AD. So AB plus BC is equal to AD. Yes, AB plus, so there's AB, plus, oh no, I'm sorry, that's false, plus BC. So AB plus BC is equal to AC. So that's false, not AD. AD minus CD is equal to AB. So let's see. AD, and then you take off of that CD. So that's going to be equal to AC, not AB, so that's false. AD, and then take away CD, okay, again, is equal to AC. Yeah, that's true. So you take away the CD and you're left with AC. AB plus BC plus CD. So AB plus BC plus CD is going to be AD. That's true. AB is equal to BC. So visually we can see this is false, but if it was hard to tell visually, the only thing we could do is take out a ruler because it doesn't give us any information about how these are spaced apart. All right, given M is the midpoint of AB, so we can draw this. Here is AB, and I'm not going to take a measurement. They just tell us that M is the midpoint of AB. So that means that the length of AM is equal to the length of MB. That's what that means. It also means that segment AM is congruent to segment MB. We might need that information. All right, if the length of AM is equal to 2x plus 1 and the length of MB is equal to 3x minus 2, then find x and AM. Okay, so we're going to use this formula here. Let's just plug in 2x plus 1 for AM and plug in 3x minus 2 for MB. And now we can solve for x. So subtract 2x from both sides. So 3x minus 2x is x. Now let's add 2 to both sides. So we get x is equal to 3. There's x. Now how do we find AM? Well, we've got AM. The length of AM is equal to 2x plus 1, but we know that x is equal to 3. So just plug in 3 for x, and you get 6 plus 1 is equal to 7. So the length of AM is equal to 7. Can a segment bisect a line? Can a segment bisect a segment? Can a line bisect a segment? Or a line. So, okay. Can a segment bisect a line? So let's draw this. Let's put some randomly oriented line. Okay. And you can put, to label the line, you can put points like this. So let's say line AB. Okay. Now, can a segment, let's just put a segment, randomly oriented, it would bisect, so this would be CD, this line. Can that happen? So this would be point P. Okay, so if the segment would bisect the line, what that's saying is that it like point P would cut the line in half. And so you might say, all right, we need to check if the length of AP is equal to the length of PB. Well, that makes no sense in the context of a line. These points here, A and B, are just to label the line. In reality, a line has there's no significant points on a line. You know, there's significant points on a segment, the end points. On a line, there's no significant points. These are just to label the line. So a line is extending infinitely in both directions. You can't, infinity is not a number. You can't say we're gonna go through the line at infinity divided by 2 or something. That infinity is not a number. So no, you can't bisect a line because a line has no unique length. So no, you can't bisect the line. Now, what about a a segment. Can you bisect a segment? So we'll do, now we're going to turn this into a segment, and we'll draw another segment, say CD. Here's point P. Yes, yeah, it definitely can. Because in this case now, if the length of AP is equal to the length of BP, then segment CD bisects segment AB. So yes. Now, can a line bisect a segment? So what we can do there is think about, here's a line CD. Yeah, yes, a line can bisect a segment. Because it doesn't matter that where the line intersects the segment. It's all about the question is this segment cut in half here? And so if AP is equal to PB, then yeah, the line bisects the segment. Line CD bisects segment AB. Now, can a line bisect a line? No, because all we have to do there is just think about, okay, here's line AB. There's these two lines. Well, you can't cut a line in half. That's the big idea. You can't cut a line in half. That doesn't make any sense. It's going infinitely in either direction. There's no midpoint. There's no length of a line. Suppose that point C lies in plane X and point D lies in plane X. What can you conclude regarding line CD? All right, so we've got a plane here. A plane is like a line. It extends infinitely. That's how you think about it. It extends infinitely in all its directions. All right, so this is plane X. All right. Now, point D lies in plane X. Okay, wait. Oh, these are, okay, it's not two separate questions. It's saying point C lies in plane X and point D lies in plane X. What can you conclude then regarding line CD? Well, that it's going to lie in plane X as well. It has to. And that's the entire line. The entire infinitely long line extends and is at all points on the line is always in the infinitely extended out plane X. Make a sketch of two intersecting lines that are perpendicular, two intersecting lines that are not perpendicular, and two parallel lines. All right, so I know when it comes to parallel lines, they have to lie in the same plane. So, and because there's you can't have two lines that aren't in the same plane and say they're parallel. So it's not enough to say two lines are parallel. If you say two lines are parallel, if they don't intersect, that's incorrect. Because you can have two lines in 3D space that don't intersect, and they're not parallel though. They're called skew lines. So if you have a line that's going up right here, and then another line that's like passing below it. It's kind of like two airplanes that they pass kind of cross, but they don't crash into each other. So their paths are parallel. Well, no, they're skew. Even though if you extend both lines infinitely in both directions, they'll never intersect. And so, is that the same idea when we're thinking about perpendicular lines? Are we thinking about how they have to lie in the same plane? Well, in that case, yes, kind of. It depends on how you look at it, but in general, yes. Because, looking at this 3D coordinate axis here, these lines are perpendicular. So this is X, Y, and Z. So the X-axis and the Y-axis are perpendicular. They intersect at the origin. The Y-axis and the Z-axis are perpendicular. And so, but you can always view this perpendicular intersection. There's a plane that you can view it in, right? So if we're going to sketch two lines that intersect and are perpendicular, there you go. But I mean, you don't have to draw it nice and straight up and down like that. You could draw it there's two lines that intersect and they're perpendicular. 90-degree intersection. Two lines that intersect and aren't perpendicular, well, just do like that. There you go. That's not 90 degrees. This angle, if it was 90 degrees, then you have the straight angle, then this angle plus this angle are the same. This is clearly, these two angles aren't the same. Now, two parallel lines, we're staying in a plane, and they're in the same plane, and they don't intersect. So, I mean, let me actually draw a plane here in 3D space. Okay, so just to distinguish these from skew lines, there's one line, there's another line. They infinitely in either direction, they never intersect. That's two parallel lines. But again, two lines that are not in the same plane that don't intersect, that's not parallel lines. All right, make a sketch of two intersecting planes, two parallel planes, and then two parallel planes intersected by a third plane that is not parallel to the first or second plane. All right, so let's see. We've got two intersecting planes would be like, there's one, and then you'd have and then I guess you wouldn't see it at the bottom if I'm trying to make this look real. Okay, and the idea is that two planes that intersect are going to intersect at a unique line. Now, but these planes extend infinitely in either direction, so does the line. In all directions they extend, so does the line. All right, now two parallel planes. Well, all right, so that's two intersecting planes. Let me do this, the part C here. Oh, so they wanted two parallel planes intersected by a third plane that's not parallel to the first or second plane. Well, let's actually, it'd be fun to think about what happens if we do a third plane here that's oriented completely differently than these first two planes. What is that going to look like? So you would have, let's see, you could do, so like that. And then you wouldn't see it. And it would kind of come through like that. You know, and you couldn't really, you see, and in this case, the intersection is one unique point. Pretty cool, right? Now, you can see it's like if you had kind of a plane that was just like a rotated version of this plane, and it was going, then it would still be just the intersection would be a line still. You know, like if you just took this plane here, you just kind of rotated it to the left a little bit. It's a different plane, but it still just goes through one line. But three completely unique planes are going to intersect at a point. All right, now let's do two parallel planes. So there's one, and then there's another. Okay. Now, you know, they extend infinitely in all directions. They never intersect. Now, two parallel planes intersect by a third plane that is not parallel to the first or the second plane. So, okay, we can do, let's see, like this, and then we'd have, it would go like that. Okay, so let's see. They would intersect here at a line. It would intersect then this second plane at another line. So like that. Suppose that planes M and N intersect. Point A lies in both planes M and N, and point B lies in both planes M and N. What can you conclude regarding line AB? Okay, so we've got plane M and plane N. intersect. So M and N, they're going to intersect at a line. Okay, point A lies in both planes M and N. So the point A would have to be on this line here. And point B also lies both in planes M and N, so it's also going to have to be on this line. And so regarding the entire line AB, well, that's the entire line's in planes M and N. That entire line is the line of intersection. Every single point on line AB is in plane M and plane N, because plane M and N extend infinitely in both directions. They're all directions. Points A, B, C, and D are coplanar. Okay, we can see that. They're in plane M. B, C, and D are collinear. Okay. Point E is not in plane M. So how many planes contain points A, B, and C? So A, B, and C are not collinear. So they're three unique points. So that's three non-coplanar points define one plane. That's plane M. What about points B, C, and D? Well, that's 3 points, but one of those points is redundant in the sense that they're all collinear. You only need 2 points to define a line, but since D is on that same line, so how many planes contain B, C, and D? An infinite number of planes. Infinite. You know, you have a line, you can draw. There's infinite number of planes you can draw through that contain this line. Okay, what about points A, B, C, and D? Well, this is the same idea. You've got there's redundancy here. Like A, B, and C are coplanar, but then point D, or however you want to look at it, doesn't go in a unique direction. So it's one plane. All right. Now, what about points A, B, C, and E? So not A, B, C, and D, but A, B, C, and E. So E replaces D. Well, E now goes in its own unique direction. So you've got 4 unique points here. So how can we figure this out? How many planes can you draw through 4 unique points? Well, we could do this manually. So a point, the plane M that's one plane. Then you could do, there's A, B, E. Okay. A, B, E. Then you've got, let's see, E, C, A is another one. And then C, B, E is another one. So that's total 1, 2, 3, 4. That's what my guess would be 4. But we can think about this from the standpoint. So we've got from that statistics standpoint, so A, B, C, and E. Okay, we're wanting to pick 3 of these. Like, how many ways can you arrange 3, but the order doesn't matter. So go to the statistics playlist if you need, but it's going to be 4, choose 3. We've got 4 to choose from. We're choosing 3 at a time, but it's the order doesn't matter in the sense that the plane that contains A, B, and C is the same as the plane that contains C, B, and A. Like A, B, C, and C, B, A, that you don't count that twice. And so 4, choose 3, that's going to be 4 factorial over 3 factorial times 4, 3 factorial times 4 minus 3 factorial. So it's 4 factorial, which is 4 times 3 factorial over 3 factorial. That's 4. And we could have done this with the idea with a line. So if we've got, how many lines go through 3 independent points? So you've got A, B, and C. How many lines go through? Well, we know it's going to be 3, but it would be 3, choose 2. 3 factorial over 2 factorial. That's 3 times 2 factorial over 2 factorial. It's 3. Using the number line provided, name the point that is the midpoint of AE. Okay, so it's a number line, so we know the distances between these points. So the midpoint of AE from A to E, and it looks like these are all equally spaced points as well. -3 to -2 to -1. Each of these lengths of these line segments is 1. So, okay, the midpoint of AE. We go 1, 2, 3, 4. 4 of these units. So C, point C, because 1, 2 on this side, 1, 2 on this side, is the endpoint of a segment. So, okay, name the point that is the endpoint of a segment of length 4. If the other endpoint is point G, the midpoint of a segment of length 4. So 0 to 3, that would be length 3 going from D to G. So, but if we go from -1 to 3, that's 1, 2, 3, 4. So segment, well, we're naming the point. So that'd be point C again, because the endpoint, if you have a segment CG, so one of the endpoints is G, and the other endpoint is C, then that segment's going to have length 4. All right, now name a point that has a distance from B equal to 3 times AC. So, okay, a distance from B equal to 3 times AC. So what is AC? That's the length of segment AC. Okay, well, we can see it's 1, 2. That's its length. You might say, what about the negative numbers? Well, no, remember, a segment doesn't have a negative length. This is just like a label, or like kind of like a coordinate system. It's if you have the front of your house and the back of your house, well, you could call the back of your house like the negative coordinate region. But if you're talking about like a length of anything, there's no negative lengths. So this is 2. All right. Now, okay, so we've got the length of AC, but now what is 3 times AC? Well, that's 3 times 2. So 6. All right. Name the point that has a distance from B equal to 3 times AC. So that's 6. So let's see. 1, 2, 3, 4, 5, 6. So H. Consider points A, B, C, and D, no 3 of which are collinear. Using 2 points at a time, how many lines are determined by these points? So we've got points A, B, and C. They're not collinear, so that means they're going to determine a plane. We'll call plane M. And then there's a fourth point that you might say, well, could that be in the plane? Well, then no, because then that would be, you'd have 3 collinear points if you did that. So it has to be non-coplanar. So now, how many lines, unique lines, can we draw? So through these points. So there's one line. There's another line. You know, there's okay. Well, we could do this manually, but just to generalize it, you use the combinations. So we've got A, B, C, and D. And we want to see how many, we're trying to count this. How many ways can we arrange A, B, C, and D? Or no, not arrange, but we want to choose. We're going to choose 2. How many ways can we choose 2 from this? But the order doesn't matter. So in other words, we're not going to say that AB is 1, count that as, and then count BA. If we were going to do that, then we would use permutation, but we're going to instead use combinations. So this is 4, choose 2. So, okay, 4 choose 2, we know is going to be 4 factorial over 2 factorial times 4 minus 2 factorial. So that's, you got 2 factorial, and then 4 times 3 times 2 factorial. So we've got 4 times 3 over 2. That's 6. So the answer is 6. Consider non-coplanar points A, B, C, and D using 3 points at a time, such as A, B, and C. How many planes are determined by these points? Okay, well, let's just come back here. They're asking same setup here, but how many planes are determined by these 4 points? Well, we just answered that a few problems ago. We do 4 choose 3, and we get 4. So the answer to this is 4. Line L is parallel to plane P. That is, it will not intersect P even if extended. Line M intersects line L. What can you conclude about M and P? Okay, that's interesting. Let's read this again. So line L is parallel to plane P. There's line L parallel to plane P. That is, it will not intersect P even if extended. Right. Line M intersects line L. So what can you conclude about M and P? Okay, maybe that they're parallel. Well, no, because we can't, there's nothing we can conclude. M might be parallel to P. It might intersect P. Because, yes, two lines, non-parallel lines, define a unique plane, but what if that plane is not parallel? We don't know the plane of M and L. It doesn't tell us anything about the plane of M and L. Because we could have a case where we've got a plane, P, and, okay, there's line L. Well, what if line M is like this? Well, extend it. There you go. But line L is still parallel to plane P. That makes complete sense. You could have a line. You could have a line L could be parallel to plane P, and you could have line M intersect line L, but still intersect line P. Okay, but you could also have a case where you have plane P, you have line L, and line M intersects line L, but it's also parallel to plane P. So we can't conclude anything about M and P. Lines A, B, and EF are said to be skew in this figure here. Yeah, you see they're skew. They never intersect, but that means they're parallel. Well, no, because they're not in the same plane. Because they neither intersect nor are parallel, but also they're not in the, yeah, right. If they're not parallel, that means they're not in the, if they don't intersect and they're not parallel, which that's the case, that means they're skew. How many planes are determined by parallel lines A, B, and DC? A, B, and DC, one plane. One plane, because you can pick, if you think about it this way, you can pick a point on one line, a point on the other line. That defines a line. Okay, that's fine. So A and B, that defines a line. But then I could pick another point, unique point, that's not collinear with A and B, and that defines a plane. All right, so we've defined a unique plane. All right, so you might say, well, let me pick another point, and so we can define another plane, but that's an issue because that any other point you pick on those lines is going to be coplanar with the first 3 points. So it's one unique plane. You can't ever pick up a point off of those lines that is not coplanar with the first 3 points you pick. You have two parallel lines that if they were coincident lines, if they were the same line, then you could only pick collinear points. A, B, and C would be collinear. But since they're parallel, not coincident, you can pick 3 different points that are unique coplanar, but you can't go any further than that. So it's one plane. All right, now how many planes are determined by the intersecting lines A, B, and B, C? Well, that's going to be one plane. Same idea. Same exact idea as what we just talked about. You can pick a point here. You could pick another point here. You could pick it, and then you could pick a third point, and it's going to be coplanar, not collinear with A and B anywhere on either of the 2 lines. But then you keep picking. You can't pick a fourth point that's going to not be coplanar. All right. What about the skew lines A, B, and E, F? That's interesting. So, all right, so I can pick a point here, A. I can pick another point on the same line or wherever. I'll pick another point here. So now we've got a line. Now, if I want to try and pick like another independent point, I don't want to stay on this line. I don't want it to be collinear. So let's come here. Okay. So now I've got these coplanar points A, B, and C. So now if I pick a fourth point, and I want to try and make it non-coplanar with A, B, and C. Can I do that? Yeah, I can. Because, here's the plane, because it's like an independent direction. So, okay, here's the plane of A, B, and C, but you see that D is outside of that plane. Now, how many planes does that determine? Well, okay, it's going to be 4. So this was 1, this was 1, and this is going to be 4. It's 4 non-coplanar points. All right, what about lines AB, BC, and DC? Okay, well, that's going to be just one plane again. So AB, well, let me just put these. It's because we haven't gone in like a unique direction. You can pick a point here, all right? Now pick another point wherever. We'll do that. So okay, we got a line. Pick another point. All right, now we've got one plane. Now let's try, if we want to make more planes, we have to, okay, wait, let's pick up, maybe, use this line. Great. Well, no, we're still coplanar. And there's nothing, we can't escape from that, so it's going to be one plane. Okay, points A, C, and H, A, C, and H, that's 3 non-collinear points, one plane. Points A, C, F, and H, A, C, F, and H, those are 4 non-coplanar points. So that's going to be 4. Okay, in this box here, use intuition to answer each question. Are line AB and line DC parallel? AB and DC, yes. They sure look like they're non-intersecting. They're in the same plane. Are lines AB and FE skew? AB and FE, yes. They're non-intersecting, but not in the same plane. All right, are segments AB and segment FE perpendicular? AB and FE, that's an interesting question. Very interesting. Because, I'm tempted to say yes. Because you can see it's like they're oriented 90 degrees apart, but they don't intersect. So, I mean, you can think about it from the standpoint of there's never going to be for sure. My answer is going to be no here. Okay, and why is that? Because if they're perpendicular, then if something is perpendicular, then there's going to be a 90-degree angle that's created. Well, there's not going to be any 90-degree angle created between these two lines, AB and FE, 100%. And I know that because the definition of an angle, you have to have a vertex. There's not going to be any. Where's the vertex going to be? They don't intersect. So for two lines to be perpendicular, they have to intersect. And those lines don't intersect, so no. Okay, use intuition once again, so just more questions here. Are segments AG and BC skew line segments? AG and BC. AG and BC, yes. They're going to intersect, or they're never going to intersect, but they're not in the same plane. Are segments AG and BC congruent? Line segments, maybe. All they're asking is the length of AG equal to the length of BC. It doesn't really look like it. So I'm going to say no, but they could be. Are segments GF and DC, segments GF and segment DC parallel? GF and DC, are they parallel? That's an interesting question. Very interesting. You might say, well, no, they're not in the same plane. Well, okay, so this is a really good question. Yes, they are parallel. And the reason is because they are in the same plane. Here's the plane. And you might say, well, wait, couldn't we have drawn a plane that contained both A, B, and FE? No, we couldn't. We could draw a plane that intersects A, B, and FE, yes. But that contains all of AB and all of FE? Absolutely not. We have a plane here that contains all of GF and all of DC. And those two lines don't intersect. So yes, they're parallel. But AB and FE don't intersect. But again, we cannot draw. We could pick, okay? You got a point here, A, B. All right, pick another point here. That's a plane. Okay, great. But then you pick another point here. That's not in the same plane. There's no unique plane that contains both lines. Yeah, I guess there's an infinite number of planes, but that's not what we're talking about. There's not one plane that you can draw that contains both those lines, like you can with, there's two parallel lines are going to contain a unique plane or define a unique plane.